Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be looking at how to use AspenPlus to do liquid-liquid extraction, and we'll be basing it on this tutorial that is created by AspenPlus. So they're going to do separation of acetone and water. They do it first using distillation and then compare this to liquid-liquid extraction. We will not be doing the complete tutorial in this video, but you should be able to find this in your library also. So the idea here is that water has a high latent heat of vaporization compared to other components, and so for the separation of water and acetone, the energy efficiency may be something that would drive you to choose something other than distillation. And so in this case, they want to look at extraction, and the way they're doing that is using 3-methylhexane as the solvent. Now, they're going to do a 50-50 acetone water solution, and they're going to be adding a separate stream of the 3-methylhexane. So let's get started in our system by opening up a new Aspen file, creating and adding the components water, acetone, and 3-methylhexane. Now you may have a little bit of a challenge finding this one, so be sure that you are using the find, and again, the tutorial will give guidance on that. For the method, we chose the Uniquac RK, the Redlich-Kwong variation of the Uniquac equation, and this is now set up and ready to go once you accept your binary interaction parameters. One thing that is going to be important in this particular case is that we want to be able to see if, with these three components, I'm going to be able to get separation. So the ternary diagram is very useful for this, and I'm going to continue to the AspenPlus ternary diagram. And this system that we're looking at is going to be at 1 bar. And just make sure you've selected the components you're wanting to use for extraction, and then choose Run Analysis. And it's not super quick, but it's going to create those triangle diagrams like we've been looking at in class. So if we look at this, sorry, it just shrank on me. What we're going to see is it will create the tie lines, and yes, indeed, we do get this two-phase region that we would have expected. So it seems like this is indeed going to be a good choice. Okay? Now, I would have expected that if they wrote a tutorial, it would be. But this is good advice for when you're not sure about your system. So now then, let's go on through. If you look through the tutorial, they're going to take you through several other things. Let's skip to page 9. And what they're going to ask you to do is to create a flow chart or a flow sheet that's going to have these various elements here. So they're going to have a series of streams and some different columns. I'm going to only focus on the column, the extractor column. They follow it up with a red radfrac so that they can complete their their separation. And they want to create and add these things. So the feed streams, all of these, I believe you know how to add. I'm going to just simply add this column extractor. So let's come back over here and go to our simulation. And we're going to find this as a separator. Okay? And you can choose that there. Under columns, we have the extractor. We also can choose our radfrac for our distillation. So we're going to add this. Well, if only it would. There we go. It finally added. And I'm going to pause the video for a moment and add the material streams. I'll be right back. Okay, so I have my various streams added. I've got a feed, a solvent, a water is going to be my bottoms product there, and the rich solvent is going to go on to a radfrac column later. We're only building this portion of it in this video. If we look at the solvent, that is at 30 degrees C in 1 bar and flows at 150 kilograms per hour. Make sure you switch to mass flow rate. And if we come back to our other feed stream, this one is going to be a 50-50 by mass mixture. Of water and acetone at 25 degrees C and 1 bar. And again, we're doing this problem on a mass basis. The flow rate on that stream was given as 100 kilograms per hour. Okay. So we now have this set up. Now it's time to look at our extractor. Okay. So the first thing you need to do is you need to tell it the number of stages. Now we've been working on how to estimate this in class. And we've seen that sometimes it's really hard to do using the graphical techniques when you get down to these very high purity systems. But in this case, they're telling us to use 8 stages, so just go ahead and do that for now. And then we're going to come to our key components. And in this case, we want to choose water as a key and the 3-methylhexane as the other key. The acetone is the one that will be traveling back and forth between stages. If we come to our pressure tab, we're going to just choose to keep this at a constant pressure of 1. And now then, we have still a red block, or red on estimates, and we're going to choose a temperature estimate that it will be approximately 25 degrees C, matching our stream temperature. Now this next step is something we have not done before, and this is to go to the Convergence tab. And Convergence is going to allow us to override this. Liquid-liquid extraction, the calculations are challenging for the computer. So we need to increase the maximum number of iterations, and they recommend using 200. And an error tolerance, they want 1 times 10 to the negative 7, so 1e negative 7. Okay, so at this point, we are ready to run this. Okay, now that does take a while. You'll notice the length of time, but we can come and look at our summary if we wish. And I wanted my results summary, my streams. And we look at this and we see that indeed we have removed almost all of the acetone from the water stream, and it is now in the rich solvent stream. If you follow along in the tutorial, they'll take you the rest of the way so that you can now use distillation and radfrac to separate this. So this concludes this video lesson, but please, again, go to the actual Aspen tutorial and you'll learn so much more. Thank you very much.